Hello students, welcome to Physical Science Digital Classes Mehboobabaad. Myself Narendra Babu Kotla, PGD Chemistry, TSMS Mehboobabaad. Today in this session we are going to discuss about classification of elements in the periodic table. In this we are going to discuss about part 5 of the topic periodic properties of the elements in the modern table. So the fourth one, ionization energy. What is ionization energy? So an ionization energy, in the sense the amount of energy required to remove an electron from the outermost orbit or shell of a neutral gaseous atom, is called ionization energy. Okay, so the amount of energy required to remove an electron from the outermost orbit or shell of a neutral gaseous atom is called ionization energy. Ionization energy means, let us take one example. This is an atom, this is the nucleus. Okay, now these are the orbits, but this is the outermost orbit, second orbit, this is the first orbit, this is the second orbit. In this second orbit one electron is present. Okay, so now this is the outermost electron. This electron is outermost electron. So that means we would like to remove this outermost electron, and to remove this electron requires some amount of energy, and that energy is called as ionization energy. So that means energy required to remove an electron from the outermost orbit or shell of a neutral gaseous atom is called ionization energy. The amount of energy required to remove the electron from its outermost orbit or shell. Okay, this is the outermost orbit or the shell. To remove this electron, we need some amount of energy, and that energy is called as ionization energy. Energy required to remove the first electron from the outermost orbit or shell of a neutral gaseous atom of the element is called its first ionization energy. For example, this is the atom. In this is the nucleus. So these are the orbits. In these orbits, this is the first orbit, second orbit. In this, for example, two electrons are present. Okay, imagine two electrons are present. This is the first electron, this is the second electron. If you want to remove the first electron, okay, so one electron, first electron from the outermost orbit or the shell of a neutral gaseous atom, okay, we require some amount of energy, and that energy is called, generally called as first ionization energy, which is also called as IE1. This is generally called as IE1, first ionization energy. Clear? Okay, and coming to the, let us see the second ionization energy. Before going to that, I will show you equation to the first ionization energy, where M is the element. Imagine now metal. Generally, why? Because metals, they lose the electrons. M means element, which we have taken in gaseous state. And if you supply some amount of energy, and requires amount of energy is called as ionization energy. Okay, and by supplying this amount of energy, we can remove the electron, and we removed one electron here. Okay, and IE is the first ionization energy, the amount of energy required to remove first electron from the outermost orbit or shell of a neutral gaseous atom. Then it formed a unipositive ion here, means it formed a cation here. And now we will discuss the second ionization energy. Now we removed the first electron here, and coming to the, would like to remove the second electron also. To remove this second electron, we require some more amount of energy, and that energy is called as second ionization energy. Means we are going to remove the electron. That means we are going to remove this electron from the unipositive ion, means from a cation, which is having the one positive charge on it. That is called as unipositive ion. The energy required to remove an electron from unipositive ion, energy required to remove an electron from unipositive ion of the element is called the second ionization energy. So here, in this case, this is the unipositive ion. Already we removed one electron, that's why it has given a unit positive charge on it. And we would like to remove one more electron. That's why requires some amount of energy, and that energy is called as second ionization energy. And it formed a, by positive ion. Okay, we removed this electron. This is about the ionization energy of, that is first ionization energy and the second ionization energy. Clear? Right. So now, ionization energy of an element that generally depends on its different factors. It depends on its different factors. Saying that the first factor is nuclear charge. Ionization energy that depends on the nuclear charge. First one. So, as the more the nuclear charge, more the ionization energy. More the nuclear charge, more the ionization energy. That means as the nuclear charge is directly proportional to the ionization energy. Nuclear charge is directly proportional to the ionization energy. So that means, let us take the example here. So this is an atom. Imagine this is an atom. So in this atom, so this is the nucleus, these are the orbits, and this is the outermost electron. Okay. Now, so nuclear charge means a positive charge. That means the charge of the nucleus, that is, increases. As the nuclear charge is more, then it attracts the outermost electron towards the nucleus. Okay. This is the outermost electron. And we would like to remove this outermost electron. But nuclear charge is very high here. As the nuclear charge is very high, and if you want to remove this electron, it requires more energy. That means, why? Because the attraction of the nucleus towards the electron is more, means the nuclear charge is just pulling the electrons towards the nucleus. That's why if you want to remove this electron, it requires more energy. So that means as the nuclear charge is high, so requires more energy to remove the electron from its outermost shell. That means as the nuclear charge is high, ionization energy is also more. Let us take the example here. So between a sodium atom and a chlorine atom. So if you observe the chlorine atom and the sodium atom, outermost electrons. So in this case, more ionization, chlorine atom requires the more ionization energy. So why? Because as we are moving from the sodium, let us consider this is the sodium and this is the chlorine. Okay. So as we are moving from the left to right in a period, the size of an atom decreases. Okay, here also. So why? Because of the increasing of the nuclear charge. As we are moving from left to right, nuclear charge increases. As the nuclear charge increases, then what happens? So if you want to remove this electron from its outermost shell, compare it to the sodium. Okay, it requires more energy to the chlorine. Means chlorine atom is having the more ionization energy. Why? Because nuclear charge is very high here. But the sodium nuclear charge is less. That's why it requires very less energy. As the nuclear charge is less, then attraction is less. That's why it requires less energy. And coming to the chlorine, nuclear charge is high, then attraction will be high. That requires more energy to remove the electron. Clear? All right. Next. Second effect is screening effect. The second one is a screening effect. This is the screening effect, or which is also called as shielding effect. So what is meant by screening effect or shielding effect? More the shells with electrons between the nucleus and the valence shell. They act as screens and decrease nuclear attraction over valence electrons. This is called the screening effect or shielding effect. What is happening here? More the number of the shells with electrons are present. If you see, more number of the shells or orbits with electrons are present. Okay, so more number of the orbits or the shells with the electrons present between the nucleus to the valency shell. So for example, this is the valency electron. Now these electrons and these electrons are the valence electrons, and Z is the nucleus here. Okay, so now, so then what happens here? Nucleus generally that shows the attraction towards the outermost electron. It shows the attraction. So like this, so it will try to pull this. towards the nucleus, outermost electron. But what is happening? So when it is having the attraction towards it, so some inner shells are also having some electrons. And due to the presence of these electrons, they act as a screen. Okay, so these electrons, they act as a screen or the shield. Okay, these electrons, they act as screen or shield. These electrons are generally acts as a screen or the shield. And due to this reason, so the attraction of the nucleus towards the outermost electron decreases. Okay, clear? That is generally called as a screening effect. So let me discuss again. More the shells with the electrons between the nucleus and the valency shells. This is the nucleus and the valency shells. If the more number of the shells are present, okay, so and these more number of the shells acts as screens. Okay, they acts as a screens here or the shield. So that these screens are the shields and they decreases the nuclear attraction over the valency electrons. And this is called screening effect. This is generally called as screening effect. Screening effect is generally inversely proportional to the ionization energy. Why? Because if the inner electrons which are present in inner shells and if these electrons acts as more number of the electrons are present, then more screening effect is present. As the screening effect is more, then attraction of the nucleus towards the outermost electron decreases. Why? Because they act as a screens and this nucleus wants to try to attract the outermost electron, but they are acting as a screen. Due to this, nuclear charge over the outermost electron decreases. Okay, that means nuclear attraction over the outermost electron decreases. So due to this, so it requires very less ionization energy. That is enough to remove this electron. Okay, okay. If this screening effect or this shielding effect is less, then requires more energy. Why? Because nuclear attraction over the outermost electron will be high. As the attraction is high, then requires less more energy to remove it. Clear? Right. That means more the screening effect, less the ionization energy requires. So let us see the example here between the lithium and the cesium. Lithium is generally having the 3 electrons and in cesium it is having the 55 electrons. Okay, the element cesium, so generally having the so many of the inner electrons in its shell, so that's why cesium with more inner shells has less ionization energy. Clear? Right. Now, next uh, feature which depends on the ionization energy, that is penetrating power of the orbitals or the penetration power of the orbitals. Orbitals belonging to the same main shell have different penetrating power towards the nucleus. Generally, orbitals belonging to the same shell, they are having the different penetrating power towards the nucleus. For example, let us take here 4s, 4p, 4d, 4f orbitals. So, in the penetration, so they are present in the same shell. So let us take the fourth shell here. Okay, this is the nucleus. Okay, this is first shell, second shell, and third shell, and fourth one. First, second, third, and fourth. In this fourth shell, s orbital is present, p orbital is present, d orbital present, and f orbital is also present. Okay, so in this, so it is easier to remove electron, so 4f electron than the 4s. Why? Because so penetrating power of the s orbital is generally having the more penetrating power. Okay, the penetrating orbitals belonging to the same main shell, that is having the so different penetrating power towards the nucleus. For example, 4s, 4p, 4d, 4f electrons, if you 4f orbitals if you take, okay, s orbital is having the more penetrating power than the p orbital. P orbital is having the more penetrating power than the d orbital. D orbital is having the more penetrating power than the f orbital. Okay, so that means so over the 4s, 4p, 4d, 4f orbitals, if the electron is present in 4f, then we can easily remove this. compared to the 4s. So if you want to remove the electron which is present in the 4s, requires more energy compared to the electron present in the 4f orbital. Why? Because this electron s orbital that can be penetrate towards this nucleus more compared to this fluorine. Okay, compared to this so f orbital, compared to this f orbital, so this they can easily penetrate s orbital. That's why. Okay, so between the beryllium, which is having electronic configuration 1s2 2s2, and boron 1s2 2s2 2p1. Okay, so that means outermost electron in beryllium that is present in s orbital, outermost electron in boron that is present in p orbital. But these the two outermost electrons are present on the same shell, same shell. So that means let us take the one more example here. So that is here. So this is two orbits are present, 1 and 2, and in this second orbit s orbital is present, p orbital is present. Okay, now s orbital is more near to the nucleus than the p orbital. Then, so if the electron is present in s orbital, it requires more energy compared to the electron is present in p orbital. That means in boron, electron is present in p orbital. Okay, that's why it requires less amount of energy to remove this. But in beryllium, electron is present in s orbital. That's why it requires so more energy to remove it. Why? Because s orbital is so more penetrating than the p orbital. Okay, then 2p is generally, so boron is generally having the less ionization energy. And the fourth one is so stable configuration. So if the electrons are present in elements which are having the half filled or the completely filled electronic configurations. Okay, if elements are having the half filled or completely filled electronic configuration, if you want to remove that electron, it requires more amount of energy to remove it. This is because, so let us see here. Example, oxygen and the nitrogen. In this oxygen, so in this 2p4 and in this nitrogen 2p3. Let us take here 2s2 2p4 and first I would like to explain about the oxygen. 4 electrons are present. 1, 2, 3 and 4 electrons are present in this 2p4. And coming to the nitrogen, so there are only 3 electrons are present. 1, 2 and 3. So in this 2p3 electronic configuration. Okay, so now if you compare, nitrogen is generally having the half filled p orbital electronic configuration compared to the oxygen. That's why, so nitrogen is having the or exhibits the more stable nature, stable configuration. That is why if you want to remove this electron, requires more energy than the so oxygen outermost electron. The fifth one is atomic radius. As the more the atomic radius, less is the ionization energy. As the size of the atom is more, then required amount of energy is less. Okay. So why? Because let us see here. So size of the atom is more. So I'm just taking the size. This is one atom and this is the one more atom. Okay. So now compared to these two, so the atom A, atom B. Atom A size is generally having the less. So means outermost electron is here. Atom B size is having more, means its outermost electron is here. So atomic size is more. That's why the nuclear attraction towards the outermost electron is less. The distance between the nucleus and outermost electron is more. That's why nucleus cannot be able to attract the outermost electron so more. Due to this, so we can easily remove this electron. And coming to the atom A, the size of this atom is less. That means electron is very near to the nucleus. That's why this nucleus can attract this electron more. As the attraction is more, then if you want to remove this electron, requires more amount of energy. This is about the atomic radius. Now, how the ionization energy changes in groups and periods, we will see. Ionization energy of the fluorine is greater than the that of so iodine. Okay, fluorine and iodine, if you compare, the fluorine is generally having the lower size Okay, and iodine size of the iodine is having the more in size. That's why we can easily remove this electron from the iodine. At the same time, ionization energy of the sodium is more than the that of the cesium. Clear? Why? Because sodium size is less compared to the cesium. Now we will discuss how this ionization energy change in groups and periods. Okay, ionization energy decreases as we go. Ionization energy decreases as we go down in a group and generally increases from left to right in a period. Why? Because so if you take a group, in a group from top to bottom, atomic radius increases, isn't it? So when we are moving from top to bottom, atomic radius increases in a group. In a group from top to bottom, atomic radius increases. As the atomic radius increases, then what happens? So the nuclear attraction towards the outermost electron decreases. Okay, as the distance between the nucleus and the outermost electron increases, attraction decreases. As the attraction decreases, then the required amount of energy is less, means less ionization energy requires. That means ionization energy decreases as we go down in a group. And coming to the period, let us see the period example here. Okay, when we are moving from left to right in a period, we discussed atomic size of that atoms in a period decreases as per our previous discussions. As the atomic size, why it decreases in the sense? So actually, so as the atomic size decreases, okay, the nuclear attraction towards the outermost electron move. The distance between the nucleus and the outermost electron is high. That's why, so it requires more ionization energy here. Clear? Right. This is about the some more explanation of it. Next, ionization energy is generally expressed in kilojoules per moles or kilojoules mole inverse. Clear? And the next one is important periodic property, that is electron affinity, which is also called as electron gain enthalpy. Electron affinity or electron gain enthalpy. So here, the energy liberated when an electron is added to the its neutral gaseous atom is called electron affinity or electron gain enthalpy. Very simple. So we have to take the condition a neutral gaseous atom. Okay. So we have to take an isolated neutral gaseous atom. So this is the neutral gaseous and isolated atom. Okay. So to this atom, to its outermost shell. This is the outermost shell. Imagine this is the first shell, second shell, and now imagine this is the outermost shell. This is valency shell. To this valency shell, so we would like to give one electron, we would like to add one electron to this outermost shell. Means the atom has to take an electron. Okay. So because of taking this electron, so this atom that releases some amount of energy, and that released energy is called as electron affinity. Okay. The amount of energy or the energy liberated when an electron is added to the neutral gaseous atom is called electron affinity. Otherwise, electron gain enthalpy. Energy is released due to gaining of the electron. That is called as electron gain enthalpy or electron affinity. If this atom it gains, or if you add one electron to this, it releases some amount of energy, and that released amount of energy is called electron affinity. Clear? So for example, so M in the sense that is the element, and to this element, if you give one electron and it becomes a negative ion, but it releases some amount of energy, and that released energy is called as first electron affinity. When you give one electron and it releases some amount of energy, and that energy is called as first electron affinity. Okay, and due to this first electron affinity, a negative charged ion will be formed. Okay, now if you want to add one more electron to this, so negative charged ion, okay, or negative ion. So the energy liberated when an electron is added to an uni-negative ion of the element is called the second electron affinity of that element. So that means the energy, so which is liberated. Again, already we added one electron to this, to the outermost shell. So we are adding one more electron to this. So then if it releases some more amount of energy, and that energy is called as second electron affinity of that element. Clear? Right. This is the uni negative ion, and to this uni negative ion we are giving one more electron, and then it releases some more amount of energy, and that released amount of energy is called as second electron affinity. And the next one is electronegativity. What is electronegativity? So the tendency or the relative tendency of its atom to attract electrons towards the itself when it is bonded to the atom of another element is called electronegativity. Simply, I would like to give the definition. Electronegativity in the sense the tendency of an atom to attract the bonded electrons towards itself. The tendency of an atom to attract the bonded electrons itself is called as electronegativity. For example, let us take, so this is one atom and this is another atom. These two atoms are in, this is the nucleus and this is nucleus. This is atom A, this is atom B. And these are the bonded electrons. Now these two electron atoms are in covalent bond now. So now, so out of these two atoms, if any one of the atom, if it attracts these bond pair of electrons little bit towards itself, and that so tendency is generally called as electronegativity. So that means, for example, if atom A is having more electronegativity, means atom A attracts so these bond pair of electrons towards itself, the bonded so electrons. Okay, so these electrons, if this atom A, if it attracts towards itself compared to the B, it is said to be A atom is having more electronegativity than the B. So now the tendency to attract the bonded electrons towards itself is generally called as electronegativity. Now, so all the factors are similarly, they influence the ionization energy and the electron affinity, and they also influence the electronegativity values of those elements. So now the Mulliken is a scientist and he proposed the electronegativity of an element is the average value of its ionization energy and electron affinity. Mulliken was the scientist and he proposed that the calculation of the electronegativity. How electronegativity we can calculate in the sense it is an average value of the ionization energy to the electron affinity. Okay, if you take the so average values of the ionization energy to the electron affinity, then we can calculate the electronegativity. This is electronegativity. Now we will discuss how this electronegativity changes in groups and periods. Okay. Before that, Pauling is the scientist. He was a scientist. He assigned to the electronegativity values for elements on the basis of their bond energies. Pauling was a scientist and he assigned the electronegativity values for elements on the basis of bond energies. Okay, Mulliken has explained the electronegativity is based on the so average values of the so ionization energy and the electron affinities. And here he has Pauling has assigned the electronegativity values for the elements on the basis of their bond energies. And he assumed that the electronegativity of hydrogen is 2.20 and calculated the values of other elements with respect to the hydrogens. And Pauling has given so electronegativity value to the hydrogen, that is 2.20, and later he calculated the so electronegativities of the other elements based on the or with respect to the hydrogen. So next, electronegativity values of elements decreases as we go down in a group. Okay, so as we are moving down the group, electronegativity values decreases. Electronegativity values decreases when we are moving from so top to bottom. Why? Because atomic size increases. as the size of the atom increases, okay, as the size of the atom increases, then electronegativity values decreases. But so if you go through the period from left to right, electronegativity values increases. Why? Because as we are moving from the left to right, the size of the atom decreases. As the size of the atom decreases, having the more nuclear charge. As the more it is having the more nuclear charge, and it attracts the bond electrons or bonded electrons towards itself. That means electronegativity values increases here. Okay, so when we are moving in a period from left to right, electronegativity values increases, but in a group from top to bottom, electronegativity values decreases. The most electronegative element in the periodic table is fluorine, and the least electronegative stable element is cesium in the periodic table. Clear? Right. Next and final concept, that is metallic and non-metallic properties. Metals generally show less electronegative character. Metals, they shows the generally less electronegative character. So what is electronegative in the sense? Metals, they do not attract the bond electrons towards itself. Actually, metals are having the nature that is they easily lose the electrons. So that means the tendency of an element to lose electron is called electropositive nature or the metallic property. Metallic nature. What is metallic nature means? An element, if it loses electrons easily, or the tendency to lose the electrons easily, and that is generally called as metallic nature or the electropositive nature. Metals are more electropositive. That means metals are electropositive elements. Why? Because almost all the metals, they loses the electrons. That's why they exhibit the electropositive nature, which is also called as metallic nature or metallic property. Okay, metallic property in the sense, so metals, they easily lose electrons. They lose electrons. Okay, so let us take the example. Let us take the example now. I'm going down in a group of the periodic table. The metallic character of elements increases as we are. Now we will discuss this metallic and non-metallic character, how it changes in groups and periods. First we will discuss about the groups. On going down in a group of the periodic table, the metallic character of elements increases. What is metallic character? The ability to lose electron or the tendency to lose electron. So if you take a group from top to bottom, let us take the example here, lithium, okay, sodium, potassium, rubidium, cesium, and francium. From lithium to the francium, as the atomic size increases, ionization energy decreases. As the ionization energy decreases means easily, so that element loses electron. Okay, if it easily loses electron in the sense having more metallic nature. So when we move down in group 1 of the periodic table, the metallic character increases from lithium to francium. Okay. So if you take any one of the group from top to bottom, metallic nature increases. That means lithium is having the least metallic nature, but coming to the francium is having more metallic nature. On going down in a group of the periodic table, the electropositive character of elements increases. Next, how this metallic nature changes in periods. On moving from left to right in a period, the metallic character of the elements decreases. Metallic character decreases, but non-metallic character increases. Non-metallic nature or character increases when we are moving in a period, along the period. Okay, let us take the example here in this third period, sodium to the chlorine. Okay, first sodium, magnesium, aluminum, they are the metals. Why? Because they can easily loses the electrons. Okay, and coming to the phosphorus, sulfur, and chlorine, they are the non-metals. So means they cannot lose electrons easily. they will accept the electrons, they takes the electrons. But coming to the silicon here, and this silicon is generally having the, so both the metallic as well as the non-metallic nature. That's why they are called as metalloids. If any one of the element exhibits both the metallic and the non-metallic nature, and such type of the elements are called as metalloids. Okay, so here the silicon is a metalloid. So as we are moving from left to right, the metallic character so decreases and non-metallic character increases. So in this third period of the periodic table, so sodium, magnesium, aluminum are metals, and the properties of the silicon are in the, so in between those of the metal and non-metal. Therefore, silicon is a metalloid. The next elements, phosphorus, sulfur, and chlorine are non-metals. So let us take the group 14 now. Okay, group 14 elements, that means which is also called as fourth A group elements. In this, carbon, silicon, germanium, tin, lead, these are the elements. And here also we know that carbon is a non-metal. When we are moving from left to right, carbon is a non-metal. And silicon and germanium are metalloids. And tin and lead are metals. If you take the group in the sense, we have to write this as carbon, silicon, germanium, tin, and lead, like that. So when we are moving from top to bottom, okay, so metallic nature, carbon is non-metal, silicon and germanium, they are the metalloids, and tin and lead are the metals. These are the metals. Silicon and germanium are metalloids, okay, and carbon is non-metal. Clear? So in a group from top to bottom, metallic nature increases. Okay, and in period from left to right, non-metallic nature so increases. So we find non-metals particularly at the right hand side top. Okay, so we find non-metals particularly at the right hand side top. At the right hand side of the periodic table, at the top we can find the non-metals, and metals at the left and right hand side bottom. Okay, so almost all in a periodic table. For example, if you take the periodic table here, so this is the a model periodic table I'm just drawing here simply. Okay, so where the non-metals are present in the sense, exactly at the right hand side and at the top of these right hand side elements, they are generally non-metals. Okay, and the left hand side, all the left hand side elements are metals. At the bottom of these right hand side elements, okay, the bottom of the right hand side elements are the so metals. Okay, in the periodic table. So that's we can explain the metals and non-metals how they are present. Okay, so thank you for watching this video.